of the school, and ex-Victoria Porozova from from Braun Labs, Wernher from Braun Labs, and she's going to talk about how quantum gravity meets the quantum computing.
Thank you so much for the introduction. In fact, I will introduce myself too for those people who don't know me, and because my history here. So first of all, I will show you the outline, so you will not get bored in the beginning, and at least I will get you interested in the topic. So this is what we are going to discuss today. Warning, since I was told 50 minutes talk, then I didn't put technicalities or formulas, because each of those topics can be taught like as a mini course. So the idea of my talk today is conceptual and teach you new aspects and new intersections between different areas of physics, and not just physics, by the way. So I am from Russia, and I defended my bachelor, master, and PhD at this university, St. Petersburg Polytechnic University. We have a very prominent Nobel Prize winner, Piotr Kapitsa. Piotr Leonidovich, in fact, worked with Rutherford himself, and he worked on super strong magnetic fields. Then he returned to Russia, and then not Russia, Soviet Union, and then they didn't let him go back. He wanted to visit parents, but they didn't let him go back. And then he actually founded Institute of Physical Problems, very famous one. And he discovered superfluidity. And as we know, superfluidity also connected to superconductivity. And we have superconducting quantum computers, right? So this is Piotr Kapitsa. My PhD also was related to Bose-Einstein condensate topic. Also, in front of St. Petersburg Polytechnic University in Russia, you have Yoff Institute. This one is a place where Soviet physics started. So all the prominent Soviet physicists, Landau, Kurchatov, Kapitsa, Frenkel. Frenkel also worked at my department of theoretical physics at Polytech. He discovered exciton. People who work with solid-state physics, you are probably well aware of excitons, right? It's a quasi-particle. And yeah, so St. Petersburg Polytechnic and Yoff, this is where I'm from. Then I went to Brazil, and I worked as a postdoc at IMPA in Rio de Janeiro. And now I work with Braun Labs and UFSCar, Universidade Federal de São Carlos. And I, as a PhD, a master, I studied interaction of light with cold atoms, Bose-Einstein condensate and Raman sideband cooling for single atoms. But I'm a theoretical physicist, so I also attended some cosmology, QFT, additional lectures. And my idea was to actually try to do some research in this area, like QFT and cosmology. I almost dropped my PhD and went to the United States, but my advisor didn't let me do this, so I actually finished my PhD, and I decided, okay, I will figure out it after. So I'm here, figured it out, kind of. So yeah, the idea is how you can connect cold atoms, quantum optics, atomic physics, and quantum gravity. It's not really trivial, right? So yeah, when I started my SciComm channel, I got many physics students. One of them was an Indian student, Abhishek, and he asked me to guide him. And together we found this project. It's called It from Qubit. It's found by Jim Simons Foundation, Stanford University, and I found it in 2021, and I didn't see anything like this anywhere around the world, just at Stanford. Like in Russia, no, they don't do this kind of type of research. So here they combine string theory, atomic physics, computer science, I don't know, all the fields of physics in this fundamental research. And the goal is to investigate quantum spacetime. So spacetime at a quantum level. By the way, how many of you know about this It from Qubit? Can you raise a hand? Okay, 1, 2. 2 people. Yeah, that's what I thought. So a lot of people here know about one of the topics we're going to discuss, which is IDS-CFT correspondence, but not many people actually connected it to quantum computing, which I find fascinating. So maybe today we'll start this type of research in Brazil. So yeah, and So Jim Simmons is my personal hero because he made contribution in theoretical physics, Chern-Simons term theory, and then he found hedge fund, became a billionaire, and then he founded fundamental research in physics. Not many people do this nowadays. Unfortunately, he passed away this year recently, and yeah. So actually, idea it from qubit came from it from bit. There is a paper about John Wheeler. So everybody probably, you know John Wheeler. John Archibald Wheeler was a teacher advisor of Feynman, of course, Misner and Thorne, and I think even maybe Hawking or Penrose, I don't remember, but the idea is that they got Nobel Prizes, but he didn't get Nobel Prize. He introduced many concepts, S-matrix, which we use in quantum field theory, wormhole. Wormhole was created also by John Archibald Wheeler, and he thought that the universe is informational. So universe observes itself, kind of via measurement, and this is how it happens. And this idea, it from qubit, the moment I saw this title, I immediately connected it to Wheeler. Of course, it's a analytical continuation to quantum space, right? From Euclidean to Hilbert. So why to say bit if we can say qubit, right? So it from qubit, this is how, I guess, guys at Stanford got the name of the project. So shortly now is going to be like warm up, right? I'm gonna brief you about quantum spacetime. So what is quantum spacetime? In classical general relativity, classical space-time is a smooth manifold, right? Described by Einstein nonlinear differential equations. It's not easy to solve them, but you can do it. And general relativity, so basically you have this nonlinear connection between mass energy, more exactly stress energy tensor, and curvature of space-time. And so curvature dictates mass how to move, and nonlinear interaction of their nonlinear interaction affects the other. And also time here. Time here is a force coordinate in general relativity. In quantum mechanics, well, the simplest, the most known Schrödinger equation for pure state, right? In quantum mechanics, we say this, we quantum physicists, right? So we say this magical phrase, nature is fundamentally quantum. Sometimes some people on my stories, they say no, or like it's not quantum, but it's quantum. Like I believe that nature is fundamentally quantum. So that's why. And also quantum mechanics deals with uncertainty principle and probabilistic description of reality. So then the question arises almost naturally, what happens with smooth manifold of spacetime? If you want to zoom in, like let's say you're going to sleep, you close your eyes and you start zooming in spacetime, in which you are all living in which you are living. So what's going on with spacetime? It's not smooth manifold anymore, but you don't know. So that's the question. That's the fundamental question of physics, right? And also pay attention that time is quantum mechanics is not relative like in general. Time is absolute and part of the background. Background is space-time. And so quantum gravity arises, right? Quantum gravity is the theory which seeks to unite these perspectives. Several approaches are being developed, and I will show you some of them. So one of them, loop quantum gravity. So shortly, space-time is made of discrete loops or networks called spin networks. Feature here is that space-time is not smooth, but instead has a granular structure at the smallest scales, the Planck scale. And there are some problems with loop quantum gravity, but there is no complete theory of quantum gravity, so it's okay. In fact, the complete theory of quantum gravity might have ideas from several approaches. So it's important to know, I guess, different approaches. String theory. String theory is a framework where the fundamental constitutions of reality are not point particles, but one-dimensional objects, but everybody knows about this. So there are strings, and vibrations of the strings correspond to different particles. And also, there is a particle called graviton. So photon has spin 1, and meson has spin, 0, right? And graviton 2. So in the book Z, Quantum Field Theory in Nutshell, there is a very awesome phrase that our reality is a subtle balance between 3 spins, 0, 1, and 2. Actually, when I asked Steven Weinberg, who united weak electromagnetic interaction, he was quite pessimistic about detection of gravitons, right? But, well, I'm more optimistic, maybe in the future. But right now, of course, we're not there yet. We have technologies like this. So space-time form is kind of just conceptual concept. It doesn't have any mathematical, like really developed framework, but it's a concept offered by Wheeler. And then holographic principle, so ADS-CFT correspondence. This one we will discuss today in this lecture. So right now is just a spoiler. We will discuss. And the last one here is non-commutative geometry. The main part here is that it generalizes the uncertainty principle, and so the operators of space-time will not commute. So it will give you, at least for me, some pessimistic perspective that some regions of space-time, they're not going to be seen as points. They're going to be, you know, like these balls of uncertainty, which means that nature will not allow you to look inside, like precisely because of this non-commutativity. You know, right? Like non-commutativity means you cannot observe simultaneously two observers corresponding to these operators. So now, the talk starts actually here. So entanglement entropy. So entanglement entropy. So my task today is to show you that there are physical quantities which we have in quantum physics, in information theory, as well as in quantum gravity. So this is the idea. In fact, we will explore this ADS-CFT correspondence, which is the result of string theory. And I call it the most successful result nowadays, because it actually unites gravity and quantum theory. So we have this entanglement entropy, and it's a quantity that measures the entanglement between subsystems constituting a quantum system. And this is the formula. I think those are kind of the only formulas I'm going to show today, mostly. So, and then, for example, if you take some separable state, so you know separable, which means it's not entangled, right? Then if you substitute these states here, you will get 0. So which means that the states is not entangled at all. But there are other types of entropies. For example, von Neumann entropy. Actually, this one we just studied. Ryu entropies. This is a generalized version of entanglement entropies, and at the limit, it becomes the previous von Neumann entropy. Moduli entropy, also important in holography and ADS-CFT, and topological entanglement entropy, and there are actually more entropies, but we don't need them all today. But you can explore. You can explore like entropies in quantum gravity and so on. So the problem is that when you need to diagonalize von Neumann entropy, von Neumann, it can become hard when you have more degrees of freedom. So it's not always sufficient. And that's why people use different types of entropies and to study the properties of entanglement. Yeah. So for example, here you can have, for example, when Q is equal to 2, it's easier to compute or measure experimentally. And yeah, so this is where it can be applied in quantum information and holography as well. In quantum information for phase transitions and error corrections and quantum algorithms. So what is the role of entropies in quantum information? So we already actually said it measures the level of entanglement, and it's really crucial for quantum algorithms because some of them require like a higher degree of entanglement to speed up, right? And also in quantum error correction codes, can you raise a hand if you know a little bit about quantum error correction codes? I think many people, no? Yeah. So it's used to protect, let's say, I would put simply, to protect your qubits. Can I say that? To protect your fragile qubits. So you can encode, for example, several physical qubits into one logical qubit and many other tricks. So yeah, for stabilization, for protection. And see, this is actually one of my favorite parts, that there are some codes that without collapsing the quantum state, you can detect some errors and fix them. It's amazing, actually. So now let's go to ADS-50. Now we go to quantum gravity. How many of you know, okay, about ADS-50? Okay, cool. So that's why I put like more slides to explain. So what is ADS? ADS here stands for anti-de Sitter spacetime. Actually, I didn't put anti-de Sitter, but anti-de Sitter. And it's a space with negative curvature. We have three possible curvatures: negative, positive, and flat. Flat is Minkowski space, zero curvature, and positive is a de Sitter space, actually, so without anti. And in a two-dimensional case, you can imagine sphere, for example. I like this picture. It's from The Science of Interstellar. Okay, everybody watched Interstellar, right? That's for sure, like you physicists. Really bad. So you have to, like, come on. How can you become a physicist without watching Interstellar? It's the best, and about quantum gravity. So there is a book, The Science of Interstellar. And there, Kip Thorne, actually he's a student of Wheeler, and he got Nobel Prize in 2017 for LIGO, for detection of gravitational waves. And I'm lucky because I got his autograph for class time like loops. But we don't like today class like time looks in this talk, so it's okay. Yeah, so what is ADS space, guys? Imagine you're a microbe, and you live on some, like we call it Braun, but you can even say membrane, for example. Yeah, so you live in this space, and you have a microbial friend. You have a friend, you two microbes. And the distance between you two, for example, 1 kilometer. In this anti-de Sitter space, if you go up a little bit, here, I thought it's 1 millimeter, it's even less, it's 0.1 millimeter, the distance between you two will shrink by 10. And then you go a little bit up, and then, so after 0.3, it will be already, what? After 0, so 100 meters, 10, it will be 1 meter. So actually, they use this kind of sandwich with de Sitter and anti-de Sitter in Interstellar to create wormhole. Like, not people created some fifth-dimensional beings, but they use this concept. So basically, anti-de Sitter space shrinks space-time for you so you can travel. Otherwise, how are you going to travel to Gargantua, to the age of the universe? It's kind of not possible. So our universe is actually de Sitter. It's actually mostly flat, so that's why we use like Euclidean metrics often, but the curvature is like 0.000 something, and it's not 0 in the end. So we say that the universe is de Sitter, but the techniques which we will discuss today, the developments, they only were done in anti-de Sitter space yet. So there is a lot of actually directions for you to explore de Sitter space itself. Yeah, so what are the key features of anti-de Sitter spacetime? So it has a boundary at infinity, and at infinity, quantum field theory called conformal field theory lives in this duality, which we will explore. Then the physics. It describes gravitational theory in a negatively curved spacetime. And there is also so-called Poincaré disk. Poincaré disk is a projective model, how you can project something. Actually, it's here. So, yeah, so I actually put here that first it was Riemann, Bertard Riemann, and then it was Beltrami, and then Poincaré. So this is how you do it. For example, you have like infinite, going to infinity some space, but your task is to project it to a unit circle. So when you're at the boundary of this unit circle, you're actually at infinity in this space-time. So it's a projective model. Yeah, the boundary represents infinity, and also the distances increase rapidly as you move away from the center, which makes sense, right? So it would take an infinite distance to reach the boundary. And quantum field theory, because our task today is quantum gravity, right? Quantum gravity is when you need to have duality between a connection between gravity, gravitational theory of Einstein, and quantum field theory, the most successful theory in physics, like quantum physics. So this quantum field theory would live on the boundary. Yeah, so geodesics. Geodesics are the shortest paths between 2 points, right? And ADS space appear as arcs within this Poincare disk. So when you see the arc, is geodesic. Also, Poincare disk helps to visualize the causal structure of ADS. Causal structure means that the signals, for example, if they were created, let's say, on the boundary, then they would have to travel, let's say, and influence events in the bulk. This is the causality principle. So, yeah. And also, there are like different types of ADS. It could be like n-dimensional, but let's say it can be 2-dimensional, 3-dimensional. Here it's 1-dimensional, always stands for time, and the rest is for a spatial coordinate. So this is how it looks like. And you can see some arcs here. This cylinder, well, I started studying this topic, but kind of slowly. Research will start like technically after this lecture. We already started, but yeah, the idea is that I think it's not trivial to understand this cylinder. The time here is compactified. In fact, it's measured in angular coordinates because we want to have this periodicity, and you have slices. So for example, this is a space slice at a certain time, and this is like you move forward. So this is a time, let's say t1 and time t0. And your conformal theory or quantum field theory lives on the boundary. And inside of the cylinder, it is a bulk, how we say, it's plus 1-dimensional. And we put here this kind of Poincare disk projection, yeah. So now, what is CFT? So conformal field theory. It's a quantum field theory that is invariant under scale transformations. Scale transformations, as you know, they preserve angles, but not distances necessarily, right? And so physics described by CFT remains unchanged under these scale transformations, translations, rotations, and physical examples of CFT is actually quantum electrodynamics, condensed matter physics at the critical points, certain string theory models. Ising model, by the way, is also example of conformal field theory. And when people do quantum computing, they really use a lot Ising model. So here you go. You actually use something from conformal field theory, and maybe you didn't know about this. So conformal transformations, well, this I just put a map. You know this probably from complex analysis, because in complex analysis you did conformal transformations, right? So you have some rotations, but locally here the angles are the same, so they preserved. So ADS, let's recap. So ADS describes gravitational theory in the bulk. Bulk we call this plus 1-dimensional, right? So plus 1 spatial dimension there. CFT describes quantum theory on a boundary. Boundary-bulk relationship is when the boundary CFT, conformal field theory, is related to the gravitational dynamics in the ADS bulk. So this is ADS CFT correspondence, or how we call it, gauge-gravity duality. So it says that gravitational theory in ADS space is dual to CFT living on its boundary. And so we have maps, actually, and we develop in maps to create this dual structure between gravitational phenomena inside the bulk and quantum field theory. If some of you are experimentalists and you will think about how is it even related to real world, there is a field in physics is called applied holography, when you can study strong correlated systems, condensed matter systems, and sometimes when you need to calculate some correlation functions, it's really hard. But you can use this principle and calculate something in the bulk, and because of this duality, basically you would have equality between two actions, like gravitational action and quantum field action. And you can use it to calculate your correlation functions. So I say that this is really success of string theory, that we have something which we can even apply in the lab. So the authors of this correspondence are these physicists from Argentina. So Maldesana, very famous paper. And the other one is Edward Wheaton. And the other one is Susskind, Lenny Susskind. Lenny Susskind gives a lot of talks. In fact, I think he's one of the leaders of this Eat from Qubit project at Stanford. So now the next one. So we need to use some formula. So the formula is this Ryu-Takayanagi formula, and it connects. This is really important. Basically, from this moment, we can start building geometry of space-time, because we introduce entropy as a measure of quantum entanglement, for example. And entropy is proportional to the area of a minimal surface in the bulk of a ds spacetime. This is a Newtonian gravitational constant. So you have here CFT, and here you have bulk, and this is some subregion A. So you have some basically area, and it spans this area in CFT on the boundary. So the minimal surface would be your gamma, how we call it. And so here it's one-dimensional, right? Because it's hard for me to put something three-dimensional on two-dimensional screen. But you can imagine that this is like a part of sphere or something, right? Yeah, so this is why area. And authors of this paper, they propose that the entanglement entropy of region A in a conformal field theory can be computed using this using the area of a minimal surface, gamma, in dual gravitational theory. And so it's actually the most important formula in this field. So because particularly in the study of quantum entanglement and geometric interpretations. For example, here, very important concept comes into the play. It's called the entanglement wedge. So it's a concept where in the context of a ds-CFT correspondence, you have already a region of the bulk space-time, which is encoded in a specific region of the boundary, conformal field theory. So what is the actually entanglement wedge? Entanglement wedge reconstruction is like another lecture, and so we're not there yet. And the idea is at least to understand what it is. And entanglement wedge is the region in the bulk that is dual to A. And the degrees of freedom in the entanglement wedge can be reconstructed from the information encoded on the boundary. When we say degrees of freedom, we mean that operators, for example. So you can have some operators or observable corresponding to some physical quantities, and you can build a map with this, like with this reconstruction, a map between the boundary conformal field theory and ADS. So the operators would have similar property. So in this is approximately how it would look like. And in ADS-CFT correspondence, the geometry of the bulk here is believed to emerge from the entanglement structure on the boundary. So this is like an important result of this correspondence principle. And for given boundary region, the entanglement wedge is the region, it is dual, and so on. That's we already mentioned. And so you can actually can construct many of them. And what happens next is that, for example, if two regions on the boundary are entangled, the corresponding entanglement wedges in the bulk might overlap, indicating shared information in the bulk. And so entanglement wedge will help us to understand how local bulk operators like gravitational fields or quantum fields can be described in terms of boundary operators. And so this is key to the idea that space-time itself can be emergent, and it emerges from entanglement. And so here, example. We didn't mention Hawking-Bekenstein entropy formula, but it's kind of similar to the formula we showed before. But at least let me give you a really interesting example with a black hole. For example, you can put a black hole in the bulk. And so the entanglement wedge of the region, so here you'd have this entanglement wedge, right? But it will include both the exterior of the black hole and the part of the bulk inside the horizon, so interior of black hole. The entanglement entropy of this boundary region contains information about the interior geometry of the black hole. I mean, this is fascinating, because how can you go inside of a black hole? You cannot. You're going to be dead. So, and we cannot even send anything, because there are no black holes in the universe close to us, thank God. So, yeah, and only in this book, The Physics of Interstellar, it's the closest moment how you get close to a black hole, when you read how Kip Thorne thinks, and they also modeled it and showed in the movie. But now we have a theory which actually can shed light on the interior of a black hole. And many people say that new physics lies inside of a black hole. So this is the way also to study new physics here. Applications of ADS-CFT. So this holographic duality, and well, about quantum error corrections a little bit later. So, and also, yeah, this concept is central in the study of black hole information paradox, because this entanglement wedge, as we saw, can help you to understand the inner geometry of a black hole. Also, there is some trick. Remember, we mentioned this Ryu entropy, and there was the index Q. So this index Q enumerates replicas. So basically, you have a method to compute entanglement entropy by considering multiple copies, replicas of a system, and then you can analytically continue the result. So, for example, yeah, and the replica trick will link this quantum entanglement and geometry of the spacetime. So the procedure looks like this. So you have multiple copies, and we have a formula. So this is actually this Ryu entropy, and in the limits, when Q goes to 1, it becomes von Neumann entanglement entropy. So you create Q copies of the quantum system, compute the Ryu entropy across the replicas, and then you obtain this one. So this trick involves calculating partition functions on this multi-level geometry, not level, but and then you have different replicas, and they are joined together at the entangling surface. The picture would look actually quite complicated. So now recap, because now we go into this quantum computing part. Yeah. So recap. We have this ADS-CFT correspondence, where we say that geometry of space-time emerges from quantum entanglement structure in the boundary. And quantum entanglement, as we think, will encode the bulk geometry. So the rest is easy, right? We just need to create some quantum algorithms and that's it. That basically you will encode your quantum space-time. Now, it's not so easy, I guess. So yeah, so this is the recap of this part. And now we go to this part. How many of you know about MERA? I think more. Oh, not, okay. So, but tensor networks. How many of you know about tensor networks? Okay, yeah, better. So MERA is a type of tensor network, and I will show you visually how it looks like. It's a powerful tool to understand entanglement structure of quantum system. And the key feature is that it's designed to represent quantum any-body systems, especially with the scale invariant entanglement. Scale invariant entanglement, it's something when, example, when you have Ising model and at a critical point, there happens phase transition, but before it happens, the system starts revealing the scale invariant properties. So that's when it becomes this CFT. And we have other types of tensor networks, like tree tensor network, projected entanglement pair states, matrix product states, and they look like this. So matrix product is just multiplication of matrices here. So H is, here we say how we define well, we can say here. For example, here it's tensor, And here you would have legs or edges, and you do summation, like concatenation of these tensors. But with MERA is kind of more complicated because the edges would be representing entanglement. So it's like a more complicated version, I guess, of this. Yeah. So how to use MERA in IDS50? Well, I put these two images for you to see the visual similarity, like between MERA, for example, how you can like encode via tensor networks, and the Poincare disk, right? So in fact, this is the idea that MERA has a direct link to IDS50 because its hierarchical structure is similar to geometry of IDS spacetime. And in particular, the structure of MERA kind of recalling of like repeating the spacetime layers in IDS. So, and also in a radial direction, each layer will capture the entanglement at a particular scale. So, and then they're gonna stack up to create the full spacetime geometry. So it's like a cylinder, and so you have these stacks of layers, right? And yeah, this is approximately how it would look like. So it's, can we say, like a simulation sort of, but this is the closest we got to use some mathematical framework for entanglement, and then connect it to ADS structure. And the idea is that the quantum entanglement in the boundary captured by MERA creates the bulk space geometry. And then the long-range entanglement is what defines the connectivity of spacetime. This is one of my favorite phrases. So when Leonard Susskind gives his talks, or Preskill, John Preskill, they like to say this: the connectivity of spacetime is provided by entanglement. It's a beautiful phrase, though, right? It's we're talking about quantum levels. So yeah, this is, I think when I first saw it, it's like thinking about entanglement from a different perspective, how fundamental entanglement is. And also, yeah, so that's what I already mentioned. Then quantum computing. So I would say this area is emerging here. Like, so I guess a lot of people can try themselves, but first I guess you need to study IDS50 correspondence. So to understand, this part is kind of hard. So the idea is that if we believe that space-time is emergent from entanglement, then we can encode the boundary, and we can use quantum information here, and we can use quantum algorithms for encoding. And so entanglement between regions of the boundary defines the connectivity. Entanglement entropy will quantify the amount of information shared between subsystems via this formula. And also it's interesting here that space-time, but this is, I think, our next one. Yeah, about quantum error corrections, I will show maybe later. So now we have tensor networks and MERA. There is a paper. And so in quantum community, people know Lukin as a physicist at Harvard, working with cold atoms, building quantum computer on atoms, right? And in this paper, he actually compared MERA and quantum convolutional neural network. This I found when I was doing postdoc at IMPA. So because I needed to study quantum convolutional neural networks, but then I saw MERA, and then yeah, and after that I studied a little bit of tensor networks. So yeah, how interesting how it's all connected. Like, and it's like machine learning, then it's quantum machine learning, but then it's actually quantum physics, quantum field theory, and it's actually cosmology and quantum gravity, you know? So, and also quantum information. So it's really interesting. Yeah. Quantum error correction codes and space-time. So there is another idea that you can use quantum error correcting codes, and bulk will behave like a quantum error correcting code, because you saw this kind of tree structures, and it's like you can use different types of quantum error correction codes. When you apply them, you can sometimes encode like 7 physical qubits into one, or like 3 qubits into one logical qubit. So you would have different geometries, and this is also the idea, I think, behind this. So having different geometries and try to also apply it. So yeah, as I said, quantum error correction codes are crucial to protect the information. And also this will suggest that space-time is inherently fault-tolerant, making the bulk geometry stable and robust to small perturbations. I think it's also interesting observation. Oh, this is a good paper, right? Because we have here Jean Presqu'île, who switched from elementary particle physics to quantum computing, because I guess all money is in quantum computing right now. So yeah, no, Jean Presqu'île, Saskind are the main people in this Eat from Qubit project. So from what I heard, like one of the main ones. And they actually investigate here holographic quantum error correcting codes for the bulk boundary correspondence. So now you can read this title and you will understand what people talk about. And this is like a visual example, some holographic hexagon state, holographic pentagon. People who know about quantum error corrections, like this look familiar, right? But it also looks familiar to our Poincare disk, right? So that's the idea behind it. And the last one, so we finishing actually. So the last one is that conformal field theories also can be simulated on quantum computers. And we will explore by doing this space-time dynamics itself, because we have this gauge gravity duality. And quantum computers can simulate the evolution of quantum states. And practical challenge here is that we need to find efficient quantum circuits to simulate CFT dynamics. Okay, so this is a future. I will show future directions in this area. So what we need to do is that explore deeper connection between quantum information theory and spacetime, investigate quantum error correction codes and how it creates the stability of spacetime, develop new algorithms, quantum algorithms to simulate CFT dynamics, and we can have improved quantum simulations of holographic theories, better understanding of the role of entanglement. Well, and if you are thinking as an applied scientist, by doing this, you can also create new quantum algorithms, new efficient quantum algorithms, and maybe you will apply them not necessarily in quantum gravity, maybe in some other areas. So it's just interesting study. For me, it's just because I like fundamental physics questions. So this is the questions created by me. So I will finish on this. For example, we know that energy is preserving quantity, and it appears like as a integral, right? It's an integral of motion, and it happens because of the symmetry connected to homogeneity of time. But if your time is emergent, because the time is part of space-time, and then what happens with energy? What is energy then? I think it's not defined, so that's one interesting question. Also, another one, if space-time is emergent, what is more fundamental than space-time? Because we live in space-time, we never think about that we live in space-time. We just don't notice it. But electromagnetic radiation, everything here, atoms embedded inside. But if it's not fundamental, it emerges, then yeah, that's a good question, I think. And entanglement is more fundamental. Let's say entanglement is more fundamental. But then entanglement of what object? So we actually need to define this, the smallest object of reality here, like to constitute space-time itself. It's also interesting. It's also not defined in physics. So basically, this is where physics kind of ends with open questions. It's like you need to build philosophy here first, I guess, some conceptual one. And I think maybe the problem with causality will happen because we don't have time. If time is emergent, you don't have time. So what about causality? And yeah. And then the other one is about virtual particles. We know that they always appear and annihilate and so on because of we have the vacuum fluctuations. But if we don't have space-time, then we don't have vacuum fluctuations. We don't have virtual particles, or do we? So yeah, that's the question. In this ADS-CFT correspondence, they don't really answer these questions. So this is the questions for you guys. So for your Nobel Prizes in physics, by the way. So yeah, but you can use MERA. MERA is kind of machine learning stuff. So yeah, that's it. Thank you for your attention and endurance during this school. And yeah, and for your attention to this topic, because I know it's kind of complicated. So thank you so much. Yeah. Teleportation. Yeah.
Is it working? All right. In that equation of entropy, wouldn't like you only consider the bulk energy? Don't you have like to consider the interface energy? I think like it's one of the first equations.
Ryu-Takayanagi formula.
I think like it's S equals to area.
Area, yeah, Ryu-Takayanagi formula. This
Yeah,
one.
that one. Don't you have like to consider the interfacial energy also?
For this part, no, they just start with the area. So they are interested in the connection, like they connect surface in the bulk and the area of it. They use similar formula in black hole, like black hole physics, like when they study quantum states, like you can connect some quantum states for a black hole, yeah. So they don't have
maybe it's
energy.
just like a silly question because I never heard about any of those things. I only studied
No,
like
they don't,
droplets.
just area, yeah.
And like in droplets, you consider like the bulk energy and the interfacial energy when
Nope.
you're gonna.
Maybe it's related to this question in the end. The energy is this kind of preserving quantity and the homogeneity of time. But I'm kind of creating right now why they don't have it, because it's a proposal by the physicists. So it is what it is. It's just fact, this formula, and then they use it to construct things. But the idea is that we actually say that at extreme conditions, energy is not going to be preserved. And so it's not kind of the fundamental thing maybe to worry about, at least here. Like they care more about their area here. So.
And I was also like wondering if you have like a triple interface, how would things work?
What do you think? It has a triple interface?
Yeah.
You
like
mean not duality?
Like a collision of two black holes or something. Then maybe each one of the black holes
they
have
like
different
they
properties.
like to build not the collision of black holes. I believe is described by classical general relativity, right? So far, it's a collision of black holes, but yeah, because of the temperatures and energies, it would be more like kind of methods of general relativity. But what they do is that they create some traversable wormholes. So they sometimes unite, they use Penrose diagrams and unite the black holes, then it goes to white hole and so on, so something like this.
So there's no connection with like how liquids work and this?
How what? Liquids?
Yeah.
How liquids work in this. Liquids is also closer to like general relativity, I would say. You're talking about Navier-Stokes equations?
No, I was like thinking about Young-Laplace equation and Young equation also. And I'm just like transposing that to that I never saw that before. And
yeah.
I only know how liquids interface works.
They like to, the idea is here not like liquids, unless they are in the specific state like superfluidity, but they use condensed matter physics here. So condensed matter physics is more applicable to this formula and to this area in general than liquids, I would say. Yeah.
Yeah, I think I like.
But you can elaborate after the talk also. It's like
right.
Yeah, investigate. But like from the beginning, liquids, first order or zero order approximation, I would say no, but maybe somehow, yeah, non-linear.
Oh, all right.
Mm-hmm.
More questions? So thank you, Victoria, very much.
Thank you. Also, we have something to show, right? So I thank you for the participation in this school. And you guys also participated in Quantum Hackathon. So there is a team who, what? Mateo, why is it like, you're not kind of, Okay. So guys asked me to put this like as a cutest logo of a quantum hackathon team. So yeah, quack. Yeah, that's it. Thank you.